The ship is humanity's first engineering attempt to give form to uncertainty. Every line upon the water is at the same time the physical expression of a risk calculation. The same sea, the same cargo, the same distance. So why does one ship sink while another enters the harbor safely? This question is not technical, but economic, because its answer determines who will invest, who will be insured, and who will dare to go out to sea. And all of these decisions have depended on the shape of the ship. In ancient times, maritime trade existed, but the concept of risk behind that trade was not what it is today. The Phoenicians crossed the Mediterranean. The Greeks connected the Aegean Islands, but their ships were built not to store cargo, only to carry it. Form was subordinate to function, and function was only movement. Risk was not calculated, it was simply accepted. Going out to sea in that era meant either success or death. For this dual fate to change, one thing had to change: the shape of the ship. When the shape changed, the relationship between water and ship changed. When that relationship changed, the draft changed. When the draft changed, cargo capacity changed. When cargo capacity changed, the probability of sinking changed. When the probability of sinking changed, the insurer set a different price. In the second millennium BCE, the trading ships of the Aegean Sea were narrow, long, and fast. This form came from the logic of warfare: move quickly, flee, strike. But trade is not warfare. Trade requires cargo. Cargo means weight, and weight made the ship more unstable in that narrow form. Every wave threatened to tip the ship over. Risk remained constant as long as the form remained constant. A change began in the Roman period. Roman shipbuilders widened the form. A type emerged with a broad, rounded hull and a deep cargo hold. This form sacrificed speed but increased stability. Stability was not merely a technical feature. It was an economic variable. A stable ship sank less often. For a ship that sank less often, the insurer demanded a lower premium. Lower premiums drew more merchants to the sea. At this point, the direct connection between form and finance becomes visible. The ship's wide hull did not only carry more cargo, it also transformed risk into a measurable asset. Measurable risk is insurable risk. Insurable risk is investable risk. This triple transformation, measurement, insurance, investment, is the core mechanism of modern finance. However, the expanded form of the Roman ship was not only about external dimensions. The number of internal cargo compartments was also a decision of form. If there were no compartments, a single breach would sink the entire ship. If compartments existed, only one section would flood while the others remained intact. This technical detail, internal bulkheads, radically changed risk. The probability of total loss and the probability of partial damage were now calculated separately. This separation is the earliest form of insurance mathematics. Chinese shipbuilders applied this logic long before Europe. In junk-type ships, watertight bulkheads were used from the beginning of the Common Era. Yet more interesting than the technology itself is its financial consequence. Insurance calculations for a ship with bulkheads differed sharply from those for a ship without them. The form changed, the risk profile changed, and financial decisions changed. By the Middle Ages, Venetian merchants elevated this logic to the level of a system. They standardized ship forms. Dozens of ships of the same size and shape were built. This standardization made comparison possible. Comparison produced price competition. Price competition created the insurance market. In the port of Venice, a merchant could look at a ship's shape and estimate its risk profile. This ability itself was a great economic power. Venice gained a major economic advantage from this system. Standard ship forms allowed insurance premiums to be standardized. When premiums were standardized, trade costs could be calculated in advance. Costs that could be calculated in advance made long-term trade contracts possible. Long-term contracts in turn created the conditions for attracting capital on a larger scale. It all began with the standardization of a ship's form. The history of Lloyd's of London reaches much later, but its intellectual roots lie in those standardized ships in the port of Venice. Lloyd's began as a coffee house, Edward Lloyd's establishment in London, where sailors, merchants, and insurers gathered. What did they discuss? The ship's shape, age, and condition. This information formed the basis of risk assessment. Information about form was transformed into insurance pricing. In the 17th century, the Netherlands took this logic even further. The Dutch built a new type of ship called the vloot. Its form was revolutionary. A flat bottom, a wide cargo hold, and a sail system requiring few crew members. Fewer crew meant lower costs. Lower costs meant lower transport prices. Lower prices meant competitive advantage. Dutch commercial hegemony in the 17th century was the economic result of a ship's form. The form of the vloot is also interesting from a modern engineering perspective. The upper part of the ship was narrow, while the lower part was wide. In Dutch ports, entry duties were calculated based on deck width. The vloot's narrow deck meant lower duties. Lower duties reduced trade costs. This design choice was simultaneously tax optimization. Ship engineering had turned into financial engineering, though very few people at the time recognized this transformation. England learned this lesson late, but once it did, it applied it on a larger scale. The British Royal Navy systematically tested ship forms. Each new form was first calculated on paper. Draft, stability coefficients, and cargo capacity were turned into numbers. Numbers were compared. Comparison determined the optimal form. This process was the first systematic application of modern engineering methodology. The material of the ship was also an inseparable part of its form. The risk profile of a wooden ship and an iron ship is completely different. Wood rots and burns, but suffers less damage in shallow waters. Iron rusts, but is stronger and can be built larger. This difference in material created distinct pricing categories in the insurance market. Material choice became a financial decision. Form once again determined economics, this time from within, invisibly. In the 19th century, the steam engine brought the greatest transformation in the history of ship form. Steamships were not dependent on sails. This meant that weather conditions were no longer the primary variable in risk calculations. Risk profiles dropped sharply. When risk dropped, insurance premiums dropped. When premiums dropped, more capital flowed into maritime trade. More capital expanded trade volume. This expansion accelerated the global spread of the Industrial Revolution. At the same time, insurance mathematics also developed. Actuaries began collecting statistics on shipwrecks, which forms sank less, at what age ships carried more risk, which routes were more dangerous. The answers to these questions were converted into numbers. Numbers made the insurance market more precise. A more precise market attracted more capital. Capital financed the construction of more ships. Form, statistics, capital. This triadic relationship is the structural model of modern finance. In the 20th century, the container revolution carried this history into a new phase. In 1956, Malcolm McLean's idea of the standardized container was the greatest leap in the history of ship form. A standard box required a standard ship. A standard ship required a standard port. A standard port made the global logistics network possible. The standardization of a single form restructured world trade. Today's global supply chain rests upon that standardized container form. The form of the container ship also redefined financial risk. Insurers could now assess not only the risk of the ship sinking, but also cargo loss, port delays, and container damage separately. This detailed assessment made cargo insurance an independent sector. As form became more complex, risk categories also became more complex. Complex risk required complex financial instruments. This demand gave rise to financial engineering. Throughout this entire history, the courage to take risks changed as a function of form. When ship form was uncertain, going to sea was the domain of the brave. When form became calculable, risk became calculable. Calculable risk became insurable. Insurable risk no longer required courage, but mathematics. This transition from courage to mathematics is the moment of birth of modern finance. The physical symbol of that moment is the changing form of the ship. Today, the same logic continues in different forms, but to see it, one does not need to look at shipyards. The aerodynamic form of an airplane changes insurance calculations. The structural form of a building determines earthquake risk. The structure of financial instruments shapes how risk is shared in the market. In every case, the same principle operates. Form determines risk determines price, and price determines decisions. Modern financial engineering itself is a matter of form. In the 1970s, the Black-Scholes model emerged. This model defined the mathematical form of option pricing. The form changed. Risk was now stored not physically, but within a mathematical structure. A mathematical structure could be measured. Measurable risk could be sold. Sellable risk expanded the market. The distance between the width of a ship's hull and the complexity of a mathematical formula may seem vast, but both answer the same question. How can we give risk a form so that we can manage it? Derivative financial instruments, futures, options, swaps are modern answers to this question. Each isolates a specific form of risk, prices it, and brings it to market. Structurally, this process is no different from the way standardized ships in the Port of Venice created the insurance market. Only the form has changed. Numbers and formulas instead of wood and iron. But the underlying logic, standardize the form, measure the risk, build the market, remains the same. The 2008 crisis tested this logic in the harshest way. Mortgage-backed securities were complex financial forms. These forms concealed risk rather than revealing it. Insurers, investors, and regulators could not see the real risk inside those forms. This blindness had consequences. Form was used not to reduce risk, but to hide it. In ship terms, this meant the hull looked strong, but there were no internal bulkheads. At the first wave, the entire hold flooded. The deepest lesson of this crisis is this: when form is not transparent, risk cannot be measured. Risk that cannot be measured cannot be priced. Risk that cannot be priced cannot be insured. Risk that cannot be insured endangers the entire system. The difference between a Venetian merchant reading a ship's risk profile from its form and a modern investor understanding the structure of a financial instrument is not technical, but political. Transparency is not a technical issue. It is an issue of power. Regulatory systems arose from this reality. The Basel Accords attempt to standardize banks' capital structures, that is, their financial form. Solvency II defines the risk forms of insurance companies. The Dodd-Frank Act regulates the form of derivative instruments. All of these are different answers to the same problem. When form is not transparent, the market cannot price correctly. Incorrectly priced risk destabilizes the system. Regulation is nothing more than the standardization of form. Climate risk opens an entirely new dimension in this context. Today, the insurance industry speaks of the largest unformed risk, the physical risks brought by climate change. Floods, storms, droughts, their frequency is increasing, but the form of that increase has not yet been fully defined. Until form is defined, risk cannot be measured. Risk that cannot be measured cannot be insured. Risk that cannot be insured lies outside the market mechanism. This means that climate risk today faces the same problem as the ancient sailor. There is no form, therefore no price, and without a price, capital does not flow. The insurance industry's efforts to give form to climate risk are, in this sense, the continuation of a historical necessity. Catastrophe bonds, parametric insurance, climate derivatives, all are attempts to give form to formless risk. Just as the Roman shipbuilders' wide hull turned an uncertain sea into a measurable risk, these instruments attempt to turn an uncertain climate future into measurable categories. Technology has changed. Necessity has not. Digital assets carry this history even further. Bitcoin's form, fixed supply, transparent protocol, immutable history defines a specific risk profile. Ethereum's form is different. Programmable contracts, a mutable protocol, a complex ecosystem. This difference in form means different risk profiles. Different risk profiles mean different prices. Different prices mean different investors. The complexity of the digital asset market is in fact the result of form diversity. It is no different from the complexity created by different ship types in the insurance market. The relationship between form and power remains constant throughout this history. Whoever defined the form defined the risk. Whoever defined the risk defined the price. Whoever defined the price controlled capital. Venice gained this power through ship standards. Britain gained it through naval technology. America gained it through the form of the dollar system. Today, technology companies seek to gain it through the form of digital platforms. Form means power in every era, in every field. We began with the form of the ship because it is the most concrete, most visible, most physical example. One can measure a ship's width, length, and depth by hand. One can infer its risk profile from these measurements. This simplicity is the key to understanding more complex form-risk relationships that have existed throughout history. Because behind complex financial instruments, digital platforms, and climate risks lies the same logic. Form determines risk. That determination makes markets possible. And markets determine who gains what. In the end, the answer to the original question becomes clear. The problem was not the sea, it was the ship itself. More precisely, it was the ship's form. When the form changed, the sea remained the same, but humans began to look at it differently. They measured uncertainty. They priced what they measured. They insured what they priced. They invested in what they insured. These 4 steps, measuring, pricing, insuring, investing, are the complete cycle of modern finance. The first link in that cycle is the wide hull of a ship. The final link has not yet been written.